Well, it's time to resume. We have a very good presentation by Leidos, so let's welcome Wayne and Humberto. So, if everybody's ready, okay, Baldwin and Humberto, I'm sorry. So, here.
Yeah, it's pretty loud.
Yeah, we're loud.
Okay.
I'm a loud guy, sorry. I'm glad.
So we're with Leidos, just a little background. We're a consulting firm. We used to be RW Back, Patrick Engineering, SEIC, and Umberto here works in our transmission planning group, and I'm in the distribution planning group. So we kind of teamed up to work on the new OSHA 269 issues that we're having. When we were doing this presentation, we were trying to think, we really wanted to focus on just the transient aspect of it. It's an EMTP conference, but I couldn't help myself. We were going to add just a little bit of the consideration you have to take to your arc flash studies while you're doing your transient overvoltage studies. So just a quick overview. I'm just going to give I promise not to bore everybody with the OSHA 269 background, because we're here to see the fun stuff. And Umberto, who's the real engineer, will give some consideration when it comes to transient overvoltage modeling and what's important to meet all the new regulations. So just a quick definition, I'm sure everybody here. So the arc flash is just the current passing through two electrodes, and that's really what kills people is the incident energy, the heat, the pressure. And the TOV is the high voltage peak during a short duration. So we're talking lightning strikes, or when you open up a breaker and you've got voltage chopping, and that's really what OSHA is going for. So why does this suddenly occur? OSHA updated a 20 or 25-year-old previous standard, OSHA 269, and now it includes electric utilities. In the past, it really stayed in the four walls inside a powerhouse, industrial. Now, transmission, distribution systems all need to be OSHA 269 compliant. And the EPRI guys made a good point. It became a scamper. So you had to do your transient overvoltage study, I believe, originally by April. Now they've pushed it back to next year, January 31st, 2016, I think. And the arc flash needs to be done by August 31st this year. Now, that's kind of backwards if you think about it, because you can't really do your arc flash study without the transient overvoltage study. I'll get into that quickly. These are the two standards that they really lean against in OSHA 269, that they tell you this is what they based a lot of their studies off of, IEEE 516 and the standard 4. Next slide. So there's two terms that seems to get people. So I tried my best to demonstrate this, because we wrangled on this for a while at our company. And is working distance and safety distance, this minimum approach distance versus like this working distance. So I'm a generation guy. So when I think working distance, I think when I have a piece of switchgear open and I'm standing in front of it, 18 inches, 36 inches. That's working distance to me. But when you think more on a transmission or distribution level, right, that's a little different. A lot of our utility clients, they have the safety distance where you're this guy and you're actually not allowed to come anywhere within this circle, this working distance. I'm sure everybody over there can see what I'm pointing at. The confusing part about the OSHA 269 is that what safety apparel this guy has to wear is based on this distance, because it's claiming that if he does any work on the energized part, like with a stick, like a hot stick or something, that the true incident energy value is from this part of the arc gap. So this distance is shorter than the minimum approach distance. And this is where I'm trying to link it all together here. So if you're going to do your arc flash study, you need to know this minimum approach distance first, right? Because then, if you see in the next slide, it's terrible. All right, so you just have to take my word for it. This is MAD, so that's the minimum approach distance we were just talking about. And the equation is MAD equals subtracts 2 times the kV divided by 10. So basically, they calculate an arc gap is, this is in inches, but twice your voltage, your system voltage, if you're single line of ground, you take the square root of 3 divided by 10. So if you go back up one more, so he's subtracting out, did you go back to the previous slide? I'm sorry. He's subtracting out this distance to get you your working for all transmission lines 46 kV and above. And what I'm trying to emphasize here is, well, you're supposed to pick out all your arc flash by August, but your transient study doesn't have to be done by January. So what are people in the industry, how are they basing this, what kind of proper PPE this person has to wear? And this is becoming a big issue from an operation standpoint. This is what we're saying. So if you look at the next slide, we've been doing this for a lot of our mid-size IOU clients. They're the ones freaking out because when you have 20 subs, it's not that big of a deal. I can do this study. When you have 400 substations, right? Now I'm talking 300 lines. Now they're like, wow, what's the quality of my data? It goes back to, how do I get my line constants in here? How do we do our studies? And if you can look at the distance, this is a standard out of their safety book. We're not allowed to tell you which line, but this is their standard that they've used for the last 20 years. You can't come, that safety, that minimum approach distance was 11 feet at 500 kV. When OSHA came through and they made an assumption on what the TOV on these lines are, if you don't do a study using fancy, clever software like EMTP, you have to use these assumed per unit values, 3.5 per unit on 138, 3.5 per on 230, and 3 on 500 kV. Umberto, I called him and I was like, is this even accurate? And he told me I was crazy. He was like, I sat in an operating room, I would never see 3 per unit. And he was waving his arms. I couldn't see it, but I assume that's what he was doing. But this is huge because we have a lot of clients with 500 kV lines. Now he's saying, phase to ground, now you're at 16 feet minimum approach, as opposed to 11 that his people are working on. I don't know about you, when I do walk downs, I'm a lot closer than that. A lot of times when I walk under a transformer, a big power transformer, you don't really think about it. If you go, they measured, our client measured the bushing to the control panel, right? I can climb up on the pad and I'm looking, that's only 8 feet, 9 feet. So now they're like, well, what are we supposed to do? So we're only gonna focus on stuff greater than 72 kV because the stuff smaller, you can tell the distances are so close that people have just adopted OSHA. It's just easier. There's no reason to stress about it. So let's say you don't want to do a fancy study, right? And we're looking at 3.5, 3. If you go to the next slide here, they give you this per unit table. So as you can tell, the smaller you get, the closer you can get the face-to-face to face-to-ground exposure. The one thing is about face-to-face exposure is generally on transmission and distribution, most utilities with working on operating practices, they cover up the other 2 phases when they work. So we're only really worried about phase-to-ground most of the time. We're struggling with some people that say, well, what if I walked underneath a takeaway in the switch open? Our argument to that is that's not a normal operation, and OSHA only speaks to what normally happens when you're out there. But these numbers so this is from 121 to 145, and I apologize, this should look a lot more clear on my laptop. It's really not that bad, even when you get to 242, I mean, you're still at 6 feet, but as you rise in high voltage, keep going over, you're now at 16 feet at 550, between 420 and 550, and then the next one, if you're so lucky to have a 745 kV line in your system, you're at 22 feet that you can't get near your energized equipment. This is, think of it this way, if you're in a bucket truck, or I don't know why you would be in a bucket truck that close, but you have to hold a stick, you go do something, that's a monster stick. You're gonna need so how do we get into these more acceptable regions, right? And that's what we strangled with, and I'm an ETAP guy, so I was like, oh, we can just put in time demand, and he mocked me, and he was like, you can't do that. So the next step that we really, before we even get there are per unit values greater than that 3.5 that we've actually witnessed, and we've called other utilities, and they're like, oh yeah, we've done EMTP studies, and we're 4 per unit. You have another special equation that you can put inside the OSHA. When you get this thing, it's pretty clear where it is in OSHA, that you can calculate all these values, and this is the T value that you guys were talking about, this overvoltage unit per unit. And that's what Umberto was figuring out in the EMTP simulations. So I'm going to tie this back to arc flash because that, to me, that's the killer. I've never really heard of someone dying of a transient overvoltage. I'm sure it happens, but I hear about people all the time, arc flash, people getting hurt. It's a balancing act. If you reduce your minimum approach distance, now your incident energy value is going to go up because you're closer to the arc, in theory. If you have really bad TOV, you're further away from the arc, but your PPE is really good. So this becomes this is an operations nightmare, right? So they want to put the guys in PPE too, because that's, your cotton shirts, your boots, without putting on the bumblebee suit, right? That's the ideal situation. But if that happens, your minimum approach distance has to be a lot further out, right? And then you can't do any work anyway. Then walk downs have become an issue. If you go the other way, and Umberto's can prove, he can get the TOVs down way, what's actually happening. If you start calculating based off of that, now you're getting you guys in a higher PPE. So it becomes a seesaw act of finding that sweet spot in your system to determine where you want to be when it comes to protection for your employees. So that's the boring stuff. He's got the fun stuff here. So, sorry, last one. So when we do these studies for our clients and people that really care about OSHA, this is what we're trying to do. We're trying to help them meet this compliance because you need to have a study in hand if you don't want to use their per unit values that they recommended. We try to look at the available resources. That means working with operations, planning, design, because we believe it's the existing stuff we can do what we can, but the future is what we can really fix. We can get your system to a good spot where you're not worried about this in the future. Hazard reductions, there's some methodology out there, and safety is really the big thing. I mean, I can't tell you how many techs I've had yell at me this past year about arc flash. Tell me this is how they've always done it. They've always stuck their heads in things, and they're grabbing bare, energized stuff. But just because you stole from the cookie jar for 20 years doesn't mean you're not stealing. So I think this is a really good thing. OSHA, I think it's been painful for everybody, but I think once we get past here, it's really going to be a lot safer for everybody.
Okay, so I'll take it for now. So he talked about the OSHA, what it needs to do. So I'll talk a little bit. Okay, so how do we actually meet that using EMTP RV? Okay, so how do we actually do the work? I'm going to give you some examples of what we have done, what we have reading so far, research that we have done. So first thing that we got a model that, I know that you guys have a translation with PSSE. Do you have anything with PSLF? Input? Nope.
That's the G.
Yeah, GE PSLF. Yeah, the West interconnection in the US uses GE a lot.
Yeah.
So anyway, so any requests for that or no?
Yeah.
Okay.
We just had one.
That's the first one.
That's not the first one.
Okay. Anyhow, so so what kind of information do you need? Usually we grab a PSSE or PSLF model, depends on the client, the East interconnection, the West interconnection. We look at the load, we look at the generation. So we get that, and we go to Cape and Ashman, depends on what you use, to get the line constant data to the frequency dependent model. So we use those two models. And the next step, like tomorrow on EMTP, how much you're gonna model EMTP? How much detail do you need to be in EMTP? How big does your network need to be? I'm not gonna build like a East interconnection EMTP. That's, so we gotta see how much. Don't wanna have too little, but don't wanna have too much. So if you go to the next, sorry, yeah, it looks pretty weird. It looks better over there on the computer. So you guys gonna have the presentation, so you see it better. But that's a very simple model that we've seen it before, which I do not recommend. They just put a line that they want to study, and they just put two sources at the end, and then you open the line. Let's have a little bit bigger, then let's have a little network. So what I usually recommend, look on your PSLF on your single line diagram. Look on that loop network and try to create the loop network. So you have a little bit more information. When you open the line, the system is still connected. It's not like isolated on an island. We still connect. So we create a little bit bigger system to be able to handle a little bit more. And we use the PSSE or PSLF, to give us the equivalent, like a little nodes or generation, to all equivalent model. We use PSSE or PSLF. And for a line constant, we use Cape or Ashman, depends on the client. So That's the first thing that we got to do, build it.
Just before he goes off that, the first thing that when we first read the OSHA, this is the first thing everybody wanted to do. They're like, well, we'll just take the 10 longest lines, we'll make one line, call it a day, and you open it and close it. And we're like, okay, we'll try that. And what you got was values through the roof. It didn't even make any valid sense. And it's when Umberto had the Eureka moment, you need the capacitance of that loop the loop network to help you out. It's more of a true representation. Once we
You don't want to be too big, but not too big.
right.
So a couple of things like we'd like to take into the consideration the studies, okay, we're gonna take a line out. So what do I measure? It's good to measure a local, a remote, and it's good to split the line. So we usually we usually split it 3 times, depends on the length. If the line is too big, you can split the line to get like halfway, 2/3 of the line to check the TOVs across the entire line. So that's something that we usually recommend, different lengths, to cut the line in between. And one thing that I would recommend first, when you start with your longest line. The longest line that you have, you start from there, on that model. Then we know that's the longest line, so that should create the worst issue. So we start from that. And what the scenarios that we did was single line to ground, double line to ground, just the ionization. And one thing that's very, very important is reclose, high speed reclose, and non-reclose. So we did those 3, single line, double line ionization for high speed reclose or without reclose. So you're gonna see, I think it's coming at, there's a huge difference when you reclose the line, high speed reclose, or the TOV.
Yep. And then per the OSHA, which references IEEE, when you do this, it's just like anything else, you need to run each simulation 200 times. 200 or 300 is the recommendation.
And that's why today I was asking about the summary for the statistical run. So we did quite a bit of those. So like sometimes you just use okay, what's the worst? Give me just a text
Right.
pad and tell me the worst, so it's easy for team.
So scripting will be helpful.
So on this one over here, the first one, they both see some 500 kV. And this is just double line to ground that gave us the worst TOV, 2.4. And then I'm gonna jump a little bit before I come back. You see on 2.4 now, you're around here, you're above 2.4. So your distance gotta be 12.6. If you're okay with that, you're seeing that you have a 13.0, that's fine. You didn't violate it. But if you have a 11.5, I'm below, I'm above. I need to do something. I'm going above. One, I go a little bit further. We'll talk about little mitigations at the end. But you see, you gotta refer your results with the table so we know where you are. And based on your own distance that you guys already have it, to see if you are far or not, if you're good or not.
So I mean, one more thing to point out is, if you didn't do any of this, you have to use the default 3. That's 16 feet. That's still a lot.
Exactly. That's a very good point.
So that's why the 2.4 was the number that a lot of our clients were aiming for at the 500 kV, because that's pretty close to their safety distances.
So by analysis, you're able to reduce from 16 to 11?
Right, because with the study, well, let me go back up. Yes and no.
Exactly. We'll talk about mitigations a little bit later. But that was OSHA was giving us. So look, if you don't want to do any study, you gotta go by that number. If you do studies, we'll go by whatever number the study number.
And that was wearing 9 cal, you said, right?
Sorry, I
That
can't.
was wearing 9 cal clothing?
Well, that has not, the distance has nothing to do with clothing, but it affects your other calculation when you do arc flash. So arc flash is instant energy, time, and short circuit. That distance gets shorter because you're minimizing this minimum approach. Now your incident energy went up. Now you're using Arc Pro, which is another testing program to do arc flash, and it's not quite linear. That's a whole nother conversation. But yeah, go ahead.
So continue, and this one, as you see, I have a single line to ground with a high speed reclose of 30 cycles, and my TOV goes to 3.5, and that makes sense, right? Because the line is still energized. So you close the line, it's still energized, so your voltage is going to go way higher. So
You have trap charges.
exactly, you have trap charge. Exactly, you didn't have give enough time to discharge.
You don't have surge arresters.
Well, exactly. Yeah, those will be kind of like a mitigation over there. Exactly. Those will be like pre-insertion. We'll talk about. So we did without. First, that's another thing. First one we did for our clients, because again, it's big clients, IOUs, they don't want to test every single line. So we're like, look, let's grab your longest line that gives you the worst, Let's not use surge arrestor. Let's not use line arrest or pre-surge. Nothing. Let's just see it how bad it is, and then we start doing the mitigation. So one thing that we did, like this one was 2.42, so it was above what the client requirement was. So we reduced the line by 5%. So gives him an idea of how long those the lines that he's going to start to worry about. So on that, when you don't do reclosing, reduce the line matter. But if you have high speed reclose, it's not going to matter. You can reduce, you're still going to see the TOB. It's not because of the length, it's because of the charge. Sorry.
So your overshooting depends on the closing time, right? How do you choose the maximum overshooting you have?
The high speed?
You have this 3.5 high.
Yeah.
That is it's not constant for different closing time.
No, that's why we do a statistical
They
run.
do a
Is it-
A statistical run to see the worst.
They switch the, I guess, the ABC phases.
Exactly.
Yeah, exactly.
So you do a lot of simulation.
Yeah, 200 simulations per.
1,000 simulations.
Exactly. I mean, it goes. Exactly. It goes pretty smooth, you know. It's just a box over there.
Actually, I presume, I'm sorry to interrupt.
No.
I presume you look at the bar chart and you can see the worst case, right?
Exactly. Yeah. So what we do, like, when we actually run, we run a statistical run, which is pretty straightforward, right? Just put the number one over there, and then that's it. It's very straightforward. And at the end, you go to mplot, you plot all of that, and then you see the bar chart that has the worst one, which one is the highest. And then you grab, so okay, I have 200. My highest was a 95 simulation for whatever reason. That was the worst. So you go to scope view, and then you grab the 95 and you plot.
What are you changing during these? I mean, are you just running the same model, the same input parameters every time?
Yes.
Because the way, so it's cutting it at different spots.
Oh, I see. So it's tripping. It's doing the analysis at a different
Right.
Exactly.
start time on the way.
Right.
To catch the worst one.
I got you.
Is it like you use the Gaussian low, I presume?
I'm sorry?
The switching of the breaker is the Gaussian low?
Yeah.
Right.
So they put a random number generator based on the Gaussian low. Because even do systematic, it will be more time consuming.
And you should disclose that force equal to 0 for the so like some just
Well, with the statistical run, you will also catch the pre-strike stuff.
Exactly.
Right, exactly.
Yeah. That's a good point.
So the thing is, fast speed reclosing is easy to kind of do because it's probably standard across, like PJM is 30 cycles. They recommend nobody follows. But when you start doing double line of ground, this is where the two worlds melt, right? Between protection and planning. How do you know how fast you're tripping on those lines? And that's where we have a third party to this team. We have a protection guy, and we go through and we look at each relay and we kind of determine the relay. And we use CAPE, and you can do the clearing content, and you start populating that into this. So this is a really interesting thing that OSHA put in everybody's lap, and it's fallen into the cracks because it doesn't belong in any department. That's what we learned. Half our clients have it in planning, the other half in protection, and both sides are like, what
Exactly.
do
We
do
have
with this?
clients that came to us that was planning group. Those clients that came to us that was protection group. Those clients that, it's like.
They're like,
okay.
just take the problem away from us.
Exactly. It varies.
Yeah.
But, so that's like, if you have high speed reclose, you're gonna see your worst TOV, for sure. So the next one, okay, so you can go back, next. We already know. A very important thing, we talked to Harry a lot about this, is the sun conduction value. If you look on the EMTP RV, when you go to the line data, that you're actually gonna put your data, you don't even see the shunt conductance input is pretty hidden on the option. And like you gotta go and check to override because they have a default value. The good thing is if you use EMTP, the default value that they have is pretty good. Based on our research that we did, it's very acceptable. But if you use it, and those shunt conduction values, is very hard to get on. There's not a lot of utility they have because you gotta go over there and measure. It depends on the type of the insulator, the location of the line, the age of the line, how much is being washed. So a lot of people go by default. Exactly. So it's very hard to get it. So a lot of people use default value. So if you're using EMTP, it's okay. The default value are acceptable. But be careful all the other softwares.
Right.
Be careful the number that you use. Double check, because these will change really your TOV. Depends on the amount that you use, you will see no TOV. So really, really be careful. Using EMTP, you're good on the number, but like double check the number. If you guys have a number, I would recommend to change it. Sorry, I like to emphasize this because we had a lot of issues with that. You know, there was a lot of work that we had to do just to make sure that we have the right shunt conductors, because we will see like a lot. You'll see no TOV, whether it's TOV and vice versa. So be careful.
And what's really messy with this number is that the newer the line, the more conservative a number you need, right? So it's the shunt conductance is almost worse. The older the line, the more pollution, the dirtier your insulators. It's a better. When I say better, less TOV.
Yeah.
You get less TOV. Yeah.
Exactly.
It leaks over.
Right.
Yeah.
Exactly.
But what do you do on a 500 kV line that goes for hundreds of miles, right?
Yeah.
Cutting through rural areas, urban area. I mean, not urban, but you know what I'm saying. It's. Go ahead.
Oh, we have a couple IEEE papers. We had a couple people that would
Correct.
talk on the industry, researchers,
Other IOUs.
Other
that
IOUs,
that do
like,
research in this.
universities. You talk to a couple people, so that's.
We just
probably
determined
better.
EMTP's number was the number, unless somebody could really argue it the other way. Give me
Exactly.
an exact number. We decided this is the most conservative value.
Exactly.
Well, this history of this number, if I remember correctly, maybe some of you were not even born. I mean, it's very old because they had a lot of tests, like in the 80s. So the Brazilians were also doing tests on the line.
Exactly. We actually have a.
EPA gave us a lot of tests.
Yeah. There is a good IEEE paper from Brazil actually. That was pretty good. That
That
helped
number
us.
kind of is an average. But you are right, when it leaks, if the insulator changes. You can also account for corona, right?
Exactly.
Yeah. So
So-
it's more complicated than you can do.
It is. And the worst part is like it's a very important number in the simulation. You know, it's a default number that we use, but it makes a huge role on the results.
So unless you have somebody that swears by some sort of tested value, we're almost just telling leave it alone.
Exactly. So
Right.
our approach pretty much, we ask the utility, do you have a number? Do you feel good about your number? If you're not, we would recommend that you use this number.
Because even if they have the number, you got to think about maintenance. Are you cleaning these insulators? You're not cleaning them. You know what I'm saying? If you had a replacement, do you even know you replaced it out there? It just, you're opening Pandora's box. I mean, don't tinker with this thing is what we're saying till you absolutely have to.
And so the last slide, I believe, before questions is, okay, mitigation, so how do you fix it? John was saying, so again, we did it without anything. We didn't do using arresters, pre-insertion, we just did the worst. And we did it the longest line to capture the worst one. So cover mitigation could be, review your high speed. But be aware that if you're in the bottom, like you're close to the limit, you're probably gonna mitigate it if you go away, if you start increasing. But it doesn't change much because the decay, it starts really on the 7 seconds. That's when you start decaying a lot, and then afterwards it still take a long time. So if you change from 30 cycles to 10 seconds or even a little bit more, if you are close to your limit, you're gonna be able to mitigate it. But if you are far, you're not going to be able to mitigate. And another thing is the high speed reclose is there for stability. Like someone was talking today actually about that. So if you're going to change that, you got to make sure that we perform stability study, dynamic studies to make sure that you're okay on changing that. On the high speed recloser is there for a reason. So maybe changing the high speed reclose, you might be open a can of worms. You're going to involve more work for you because you're going to have to do other things that was there for a good reason. So that's technically not our best mitigation, I would say, unless you're very close to the limit and changing a little bit would fix, but I would not recommend it. The other one, like he said, is the line arresters, surge arresters, and the pre-insertion resistors. Another thing is it then start becoming more expensive way. You use you can change transmission system to minimize the effect, but then you start getting a lot of money involved. So I feel that the pre-insertion and the arresters do a good job. They will do a good job on mitigating those issues.
I mean, we went through thousands and thousands of studies, and Umberto put the resistor in and out, and that helped. if high-speed reclosing wasn't part of the equation. High-speed reclosing is part of it. Pre-insertion, none of this stuff, it makes no difference. So that's something you really want to keep into.
And again, any choice that you pick, revise with EMTP. If you pick a race or whatever, redo the work,
Right.
test to make sure, and emphasize the high-speed reclose. If you're thinking about changing the high-speed reclose, you gotta do PSSC or PSLF study to make sure that your system is not gonna be adversely impacted.
So if you have this issue, you better buy EMTP before January, because you need to do this study.
And now you realize, David, that they are playing with human life. If somebody dies,
They are heroes.
So we have to put maybe in the
Disclosure, exactly.
disclaimers.
Yeah, put that. That's a good one. Go ahead, guys.
OSHA does not, this is for maintenance purposes, OSHA does not recommend that you allow reclosing.
Right.
for Maintenance, so you've added it. Why?
Because we had
It's
a
during maintenance only, it's not just to find a TOB.
So-
There's two divisions.
right. So a lot of times, what he's speaking to is like a lot of times when you're on these transmission lines, they get what they call the green tag, I think, or some sort of tag, and you're not allowed to do any switching.
Right.
Right? We have a client that doesn't have the best procedures for that. You would think it would be very,
True.
you know what I'm saying? Like when they have projects, they sometimes lose track of what shouldn't be switched.
That's poor maintenance.
I agree, but we're playing with human lives now. So they were like, we wanted to do at least an N-1.
And,
If we,
and to his point earlier, that the default creep per unit is 22 feet. Well, you could be just in the station, not working on.
No, I mean, we're talking about portable gap devices as well as insulators.
right.
Is wherever you get arc over, okay, chances are there's arc over in a substation a lot closer than 15 feet, okay?
Yeah.
Think about what you're really talking about. Number of steel structures and everything, there's got wire. So in a substation, I don't think you can have that issue. There's plenty of protection as you come in. What you're really talking about is tower maintenance. And you use portable arc gap devices and what have you
Right.
out in the field. I don't think it's so much an issue in a substation.
Yeah,
You got arresters and everything for this stuff.
I agree. I mean, but I can tell you that the way some of our folks have interpreted that is they would want it within the station too.
Well, get PE to sign off otherwise.
I guess one question I had is, the worst case line in your system,
Mhm.
longest line or whatever, at a certain voltage, is that adequate in your opinion, or do you need or does the standard say you've got to do every line regardless?
It's just that it has to be a study, a study that basically your peers would agree that this is a valid study. And that's why when Alberto says he takes the worst line, does this study, and starts cutting the line back 5%, 10%, until he gets into a good value. Now he's got some sort of benchmark
Exactly.
along your system. What's the length of that line? Because the line length is a big difference.
Yeah.
So then he starts saying, well, wow, I'm at 50% of the line, I'm still got terrible TOV. Then he starts looking at more lines. He starts opening it up. But if he's at that long line, and we're not just picking one line. If you have like
Exactly.
30 lines, we're doing at least 10%. All various regions, and we start benchmarking it back and back.
Exactly. I would not recommend just do one. We do couple, like we did couple loops. Doing a lot is a lot of work. Like if you do a couple different locations, I don't know like how big your system is. So your system might be too big all over the place. So you grab a couple loops here in the north section of your, the south section, and then you do it. And then you start reducing age to see like, okay, so, oh man, I reduced 75% and we still have an issue. Oh, I have a lot of lines like that. So like, yeah, good luck. You're gonna start having, But like if I reduce 5%, 95, I'm good. I do 9, I'm even better. It's like, so like, okay, I can start feel more comfortable with the results. But I would grab different like loops of your system. Depends how big it is. Right?
So this is a big problem because the date was originally
Exactly,
May
that's what I'm
1st or something like it. It was actually further up in the year.
April,
So,
April.
so we talked to somebody at Epri, we were like, well, we're just not gonna make it, right? So then we had to take a sampling size, and now they moved the date back, so now we have time with some of our clients, we're going back, fine tuning our models, trying to add as many loops, variations. But going to your point, I agree. If proper operations, you're not going to have that switching.
Exactly. A lot of
principle.
people disable high-speed reclose, right?
Right.
During.
No, that's fine. And they allow you to do it. All they ask is if in your analysis, and they do have high speed,
Right.
then you just include it in your
Right.
recording. So you are correct. You can do it that way. You just have to state that.
Right.
What you know. So there's nothing wrong with that. It's just that I hope they do it the right way.
Exactly. It's life.
Reclose, you know?
Right.
It's life threatening.
We also have to understand too that typically one of the major things that they're getting close to these lines for is a line control after a fault operation. So if you have the lightning and it's automatic reclose, I go out to patrol the line, it's a 70-mile long transmission line. I
Right.
don't know if all that many people that send an operator to the other side of the 70-mile line and cut out and closing to do their line control.
Exactly.
Just because.
You pick.
No.
One thing I'd like to add in addition to line length, one thing that we've discovered is that one factor that's very important is the number of transmission lines for at the sending end. If you have, let's say, just a radially fed
Exactly.
transmission
Right.
line from a transformer, what's going to happen is you'll send a traffic wave down the line, reflects back, it's a transformer doubles versus station with a lot of lines, whereas it'll go down, come back,
Right.
distribute back into the system. So that's one factor that you've seen kind of not so highlighted. There's a lot of importance led to the line length, but I think that traffic wave propagation is really one of the big driving factors that makes line length not just the only
Right.
adequate measure for this.
Well, to your point, if a lot of these situations are post-fault inspections, then, I mean, what you said about, okay, let's assume there are no arresters on the line. Well, what if some percentage of them are compromised, or your
Right.
insulation is somewhat compromised because that was the genesis of the fault to begin with?
And a study like this really helps them with their capital projects, right? So it's one of those things that we show this, you got issues, they go out, they can add it to next year's projects list.
Exactly.
So you really help, and you start adding it to your standard designs. I mean, we have a client that's now makes this their standard package. There's one last thing I wanted to add. We really emphasize 500 and 230 kV, but because of this high-speed reclosing, we've seen people with high-speed reclosing at 138 kV, so that TOV did jump way up, and it did become an issue for them as well. So that they got headaches.
Exactly. So like that was to your point if there's no line arrest. So we start having issue. There was a couple clients that you will reduce, and then they ask to do more because like, oh, what about the line? We don't have a raster. They're pretty much the same size. Yeah, let's do it before you go ahead and buy it.
Right.
Right. So maybe it's cheaper just to do the studies. It's like it's worth the risk. It's like, oh, I don't have those arrests. They're pretty much the same length. Can we test that loop? Can you test that line? Yeah. Okay. So, Henry, sorry.
Yeah, I had a question, but I think actually Jean told me you answered already. It was, do you study the case when if you reclose your line, you have a TOV, and if you open the line during the TOV, you might have more than one PU in the trap charge in the end. Do you study those cases?
So like you open, you reclose, you
So
open
you
back.
So you have the trap charge
Yeah.
around one PU, then you reclose, and let's say for whatever reason you open during the TOV. So you
No.
might open during an
No, no, no.
overvoltage
No.
and have like 1.5 or 2 PU trap.
No, we didn't test that. We just tested like.
Closing the trap charge.
Yeah, we're
It's, wait,
On one PU open. Let's say they open, they're gonna have the overvoltage, and for some reason they open during this overvoltage and they have one.
exactly. It's gonna be even higher, right? Because it's already there. So like,
And
it's
so after
accumulated.
if you close again, you're gonna have
Exactly.
worse overvoltage.
Exactly.
Very interesting.
Yeah,
It's a
yeah,
good
good.
Exactly. Very interesting. Thank you very much, Valerie. Thank you, Humberto, for this good presentation. So now we have Tom Solinsky from Sacri Nuclear Engineering. So we have a lot of customers in the nuclear industry who are using ENTP-RB, and they need a commercial grade dedicated version of ENTP-RB for open phase analysis.